Hello, everyone. Yeah. So as you mentioned, we will talk about normalizing flows. And I think Rihanna also talked a bit about this in her last session, but hopefully we'll be able to go a bit more in depth here. So the approach we'll take is in the beginning, we will try to develop the basic math, understand the framework. We'll move a bit slowly and try to build intuition. And there will be some pen and paper exercises along the way, some short ones, so you can kind of follow along. So you might want to have a pen and paper ready. And then after that, we'll move to more kind of practical, how would you implement this kind of stuff? And then we'll have a coding session. And I think we'll spend maybe 45, 50 minutes. So that will be kind of like a break in the middle where you can do some coding. And then towards the end, we'll look at more kind of recent exciting developments. And here we won't go as in depth. We will more like, I'll give you like an overview and maybe pique your interest so you can go read the papers more on your own. And then if we have time in the end, I think we'll have a little bit of time, then there will be a bonus part where I will also talk a bit about connecting this to variational inference, just how to apply it there, really. We'll focus more on kind of generative modeling throughout the beginning of the talk. So where are flows useful, you might ask? And it's really anywhere you need a flexible density px, which has two main or two things you can do with it. Number one, you can sample from it. You can generate samples. And number two, you can compute the log density. So if I give you a point x, you can tell me what the log probability of that point is. And when you're using flows, you're typically interested in at least one of these or both, often both. So one example where a flow might be useful is this kind of toy density on the right here. If you're trying to model some very complicated density like this, obviously using a Gaussian won't work very well. And so you might think, okay, can I use like a mixture of Gaussians or something? But it's still going to be like, really, you're going to need a lot of components and it's going to be difficult to fit. So, but this is like somewhere where using a flow might be useful. And this is the density you'll actually try to model in the toy or in the coding session later. So why flows and not these many other types of flexible densities? Flows have the benefit that you can compute the exact density, and typically you can do it fast, a bit depending on how you structure the flow. We'll get back to this, but typically you can do it fast. And also you can sample, also typically fast. So that's a big benefit. If we compare it to autoregressive models, there you can also get the exact density and typically fast, but sampling is slow because you will have you generate like one dimension at a time. VAEs also have fast sampling, but for the density, you can compute it fast, but you only get an approximation. You get the lower bound, the elbow. And then we have GANs. There you can also generate samples fast, but they don't even have any form of density estimate. And that's like, even in theory, you often can't compute it because it has a lower dimensional support than the space you're working in. And so anywhere you try to ask for the density, there might not be any mass there. And then there's EBMs. They're kind of hard to work with in every way. They provide only a normalized density. So it means you can only kind of compare the density relative at 2 points, but the density at any one point, that is intractable. You don't know the normalization constant. And then sampling is also intractable. You typically have to resort to some kind of MCMC method or something like that, and then run it for a number of iterations. And then, of course, in practice, you always have to truncate early. So you will just get approximate samples. And it's also kind of slow because you have to run usually quite a few iterations. Finally, DDPMs or diffusion models, score-based models, they're also you get a lower bound on the density as in VAs. And it's maybe a bit unfair, but they're usually kind of slow because typically you work with thousands of layers. So if you want to generate a sample, you have to loop through the thousands of layers. And the density is also slow because you also have then to compute it for all layers. That said, when you're training them, you can Monte Carlo sample layers. So you can actually compute kind of a stochastic estimate of the density even faster. And that's what you use during training. So they're actually pretty fast to train. But when you want to do like the test log likelihood at the end, then it's pretty slow. So it might seem for this that flows are just better than all the other models. And that's not the point I'm trying to make. But I'm just kind of showing you that the benefits of flows and how they compare to other models in those respects. You could probably compare them on more axes and you would find different models are good. So I mean, if you want to have really good log likelihoods on, for example, images, then autoregressive models and DDPMs are usually the ones that give you the best performance there. And if you want to generate nice images, then typically also GANs and DDPMs are better. And if you, like with VAs, you can probably learn compressed representations and so on. So there's, of course, many reasons to use other models. But flows have this very nice property that you can actually compute both the density and sample fast and exact. And that makes them so you can use them for generative modeling, and also they're very useful for variational inference and many other applications. So before we get to the outline, this is just like a little background before we get to the outline. I'll provide just a little bit of historical context. So normalizing flows, the term originates from these papers from Tabak and collaborators. It describes the change in probability density as you pass samples through a series of invertible maps. And the term was, I think, really popularized in this paper by Resend and Mohammed, where they applied it to variational inference. So they try to have more flexible posterior approximations in a variational autoencoder. And so this is like some example from their paper, these toy densities, and you can see as they stack more layers of invertible maps here, they approximate this distribution better and better, these different toy densities here. And also they use it in a variational autoencoder, and you can see that the negative log likelihood goes down with more layers of flow. Kind of independently, this was developed in, or normalizing flows were introduced for generative modeling by Din et al. In these two papers, NICE and Real MAP. And they considered, generative modeling. Interestingly, they didn't call it normalizing flows. If you look in these papers, you won't say flow anywhere, but nowadays people will call it flows. It fits into exactly the same framework. And here's the first example of that. This is CFAR10 samples. You could say what you want about those, but I guess it was early days of generative modeling and a new type of model class. Then it was improved in this paper that came after, Real MAP, which is maybe a bit more famous now. And here they improved a lot on the previous model. And they also generate kind of nice faces. So this is actually the type of model you will implement later in the programming exercise. So here's the outline. For the rest of the talks, I've divided the talk into 4 parts. And they're not of equal size at all. We will spend more time on the first 2. And in the second part, we'll have a coding exercise. So first, we'll kind of introduce the framework of normalizing flows. This is where we do kind of, like how do we construct densities using these invertible maps and change a variables formula and so on. And then we'll look at these coupling flows and autoregressive flows, which are more like practical ways how you would structure it to actually be able to implement it. And then we'll look at these more recent developments, continuous time flows, where you use a differential equation to describe the transformation, residual flows where you use invertible rest nets, and then discrete flows where you work on discrete data, and then surjective flows where you can use transformations that are non-invertible in your flow. So the flow framework. When you want to construct a density px, flexible density, yes, question? Yeah. I think most people use flow just as a shorthand for normalizing flow. You don't want to say it all the time. So I would think that's the main reason people say flow. Yeah, so when you want to construct a density px using a flow, you use two main components. The first is a base distribution, p set, and then you use a mapping f. It looks like this. You have the base distribution up here. This is typically a simple distribution, like Gaussian. And then you have a mapping that is typically a neural network that morphs this kind of simple distribution into a more complicated distribution. So if you want to generate a sample from this model, you sample first from the simple distribution up here. So you sample from your Gaussian, and then you pass it through the neural network to get a sample X. So that seems simple enough. And this, you might say, this reminds me of some other models I've seen. It might remind you of VAEs, and it's quite similar to VAEs, except there you have like a conditional density here. And so, I mean, that comes with its own set of problems, intractable inference and so on, but it also, of course, makes you freer, as we'll get to later. And you might also say, this reminds me of GANs. This looks exactly like GANs, and that's true. Everything on here is also true for GANs. So the main difference to GANs is that we have another requirement. We require f to be invertible or bijective. That means we can not only can we map from set to x, but we can also map from x to set. And that's useful for computing log densities, as we'll look at soon. But before that, we'll remind ourselves invertibility quickly. So you all have been taught this before. You all probably know it, but I think it's still good to recap a little bit. So if you have an invertible mapping between two spaces, x and z, that means that for every point in x, you can find exactly one point in z and vice versa. So you could say that they're kind of equivalent representations of the same data. So if you have data x, you can map that to z, and then you have an equivalent representation. You can always map it back to get the same data. And so in the transformation, there is kind of no loss of information. And I always like to look at the simplest possible example, and that is in 1D. So in 1D, this is an example of an invertible function. Every point in x maps to one point in z, and vice versa. Here's an example of a non-invertible function. It bends back on itself. So at this point, there's like 3 possible x's that could have resulted in this y. So that's not invertible. Although also, it can't go flat like this because this one set corresponds to many possible x's, not invertible. So it seems we have found the rule. It has to be strictly increasing. But there's also one more possibility, and it can be also strictly decreasing. That's also fine. So that's in 1D, what the requirement is. So you might say, can we plot this in a higher dimension than 1? And unfortunately, that's difficult because already in 2D, this would require a 4D plot. So it's kind of difficult. But I think this figure on the left here should kind of show like the general case. Okay, so that's the invertibility. So we can use this to compute the density. So if we wanted to compute the density of a point x, we would do the following. First, we would project it from x to z using the inverse map. And then we can evaluate the density of the Gaussian up there, or the density of the point under the Gaussian. And it might intuitively seem like we should be done, but no, there's one thing missing. It's the Jacobian determinant term. And this describes kind of the volume change in this transformation. So let's look a bit at this term also and see if we can get some intuition for what this means. So again, let's start in 1D. It's the simplest possible case. So this is what it looks like in 1D. There's no determinant. We just have, yeah, I forgot to mention that this is, yeah, I think this is the change of variables formula. Yeah. So in 1D, it looks like this. There's no determinant. It's just a derivative of set with respect to x. And what I want you to do now is try to derive this. Wrong way. There. So we'll take like 5 minutes, and you can see if you can try to derive this. I'll give you what I think is a good starting point. So we can say that if I integrate p of x on the x-axis from x1 to x2, that by definition should be equal to the integral of p set on the z-axis from set1 to set2. And remember, there are two possible cases. So you can be strictly increasing or strictly decreasing the invertible map between them. So yeah, we can take about 5 minutes, and then yeah. So I think maybe we'll cut it there and continue. So the first thing you might do is kind of multiply and divide by dx, do a change of variables. And you can see that if we equate these two terms, we have almost what we're looking for already. This px is the same as down there, except the absolute value sign. So what's missing? Well, we have to be a bit careful about the integration limits here. So there's two possible cases, as we mentioned before. In the increasing case, you can see that set1 maps to x1 and set2 maps to x2. And so you get kind of the straightforward thing. And then there's the decreasing case, and here you see that set1 maps to x2 and set2 maps to x1. So you get kind of the order flipped. So in the integration limits here, they will be flipped around. And so if you know your integrals, you know that you can easily fix this. You can flip the order back if you negate the integral. So that will look something like this. And then we can combine the two. So remember here, the derivative is positive. So this is positive, and here it's negative, but we have minus that. So it will be in total a positive quantity. And so the easy way to combine the two is just to have the absolute value. So that's the, yeah, one way to derive it at least. So that's nice. We've derived the change of variables formula in 1D. Can we get some intuition for what this term means? So let's look at an example known as inverse transform sampling. You might have come across this in some statistics course you've had. It says that if you want to sample from a distribution, you can always sample from a uniform distribution and pass that through the inverse CDF of that or like corresponding to that distribution. So if you ignore the colors and look at this figure here, here we have kind of a uniform distribution lying on its side. And if you sample from this and pass it through this inverse CDF here, you map down here and you get samples according to this PDF down here. So one thing to note here is that the uniform distribution will always be 1. So we can simplify this expression. And we see that the density down here, the PDF, is actually dominated only by this Jacobian determinant term. As you see that when this is steeper, the CDF, more mass will hit here, and so you will get like more mass accumulating here. Whereas when it's relatively flat, like here, little mass will hit it, and you get less mass down here. So that's one way to get some intuition for this in 1D. And you might also, I mean, we know that the CDF is strictly increasing. So if you remove the absolute value signs, this is actually also the definition of the PDF. That's just a side note. So we're typically not interested in the 1D case. So what about when we go to higher dimensions? Then it changes like this. So you have the determinant of the Jacobian matrix. The Jacobian matrix is a D by D matrix, typically denoted J for Jacobian. And it's a matrix of all the partial derivatives, or the partial derivatives of all the outputs with respect to all the inputs. So if this is your bijective transformation, then yeah, it's the partial derivative of all the sets up there with respect to all the x's. And then you have to take the determinant of this, then the absolute value, and that will be like the volume correction term in multiple dimensions. So we're not going to derive this, but you will just have to trust that this is correct. So that yeah, that hopefully you gained a little bit more intuition about this formula. So this is that force change of variables formula in log form. So what I'd like you to do now is maybe take probably like, let's say 3 minutes or something, and try to think about how you would compute this in deep learning software. If you have a favorite deep learning framework, think in that. And I give you F inverse, the function implemented. You can use autodiff on it. And I give you a minibatch x, and I want you to give me the gradient of log px, like with respect to its parameters. Can you think of kind of in pseudocode like terms, how would you go about computing it? And it's supposed to be hard. That's the point I'm trying to make. But you can just think for a little bit, and then take like 2-3 minutes. Okay, so I think we'll just continue from there. So if I give you the function, what you could do is take the x, pass it through to set. You could compute the density under the Gaussian. That's simple. And then you have this term. And if you want to compute this in a black box way, you would have to compute the Jacobian of the transformation you did down here. So that's an expensive operation. You typically don't compute full Jacobians in deep learning software. It's doable, but it will be quadratic in the dimension, an expensive quadratic. And then after that, you have to compute the determinant, which is cubic in cost in the dimensionality. So it's really expensive for higher dimensional data. And then, of course, the absolute value in log, that's trivial. Now you have log px, and now you want to compute the gradient of that. So now you have to backward propagate through the computation graph of all of this, and it will be really, really complicated and heavy. So you don't really use black box invertible functions and use autodiff to get this Jacobian determinant here. This you have to structure the flow somehow so that this becomes easier to compute. That's what we'll look at in the next part. Before that, I just want to make one more point. And that's, so this is just the same as the previous slide, just shifted to the side. And the point is, if you want to construct a flexible transformation, a flexible bijection, one way to do it is to stack multiple bijections. So this is a very nice property. You can simply do like this. So here, the forward transformation in the sampling becomes, I mean, just a natural thing. You pass through them in the order 1 to t. Inverse, opposite order, you pass through their inverses. And then the very nice thing is that the Jacobian determinant also decomposes into a sum of the log Jacobian determinants for each of the terms. And you can see this is not hard to derive from like the chain rule of calculus, properties of determinants, properties of logs, etc. And so that's super nice because it means we can, instead of trying to create one very flexible transformation, we can focus on creating these modules, these layers that we can compose together to form flexible densities. And the kind of what I've underlined here is the three main things you have to implement if you want to make a new flow layer. You need the inverse transformation, the forward transformation, the inverse transformation, and the Jacobian determinant. So that takes us back to the outline. So I'll keep coming back to this to kind of fill in a little summary and look ahead in between the parts. So far we developed a framework using invertible transformations to build flexible densities. You can sample from them, compute the density. They have three important parts: forward, inverse, Jacobian determinant. And now we'll look a bit at some layers you can construct to use in flows that have these cheaper to compute Jacobian determinants. So how to build efficient flows? We want to make these flow layers. We want them to have 3 properties. We want them to be expressive, so they can perform some non-trivial transformation of our data. Number 2, we want them to be invertible. That's a requirement. And number 3, we want them to have cheap to compute Jacobian determinants. So here's a figure from the residual flows paper by Chen et al. They nicely categorize different flow layers into some categories. So the first one is called determinant identities. They typically rely on some form of low rank structure in the Jacobian to make the Jacobian determinant cheaper to compute. And in here we have planar and radial flows. They come from the original Mohammed and Risenda paper. And then Sylvester flows is actually by Rihanna, the previous speaker, and collaborators. Unfortunately, I won't go into this class of flows today, but we will look at the other ones. You can, of course, look at the papers more if you're interested. Yeah. How would we decide on the best flow between X and Z? I mean, you can develop many types of layers and then compose them together, and we'll talk about some layers now soon. And so, like, how would you decide? Is I guess it depends on, like, do you want fast sampling? Do you want fast densities? What type of data is it? You would maybe structure it a bit according to that. But in general, it's hard to say. It's like when you build a neural network. How do you want to build a neural network? It's always some creativity that comes into the process. Yeah. So the second class, autoregressive flows. In here you find masked autoregressive flows, inverse autoregressive flows, etc. And they rely on transforming one dimension, or transforming each dimension conditioned on the previous dimensions. And they thereby get a lower triangular Jacobian. Next, coupling. Also a lower triangular matrix. They introduce some more sparsity, which essentially makes it so that you can compute the density and sample fast. And we'll look at this soon. And in here you find nice and real MAP that we mentioned before, also that you'll implement, and then also glow and flow plus plus, and so on. And then there's the final category. In the paper here, they called it unbiased. So that's the residual flows paper. They can have a dense Jacobian and then have like an unbiased stochastic estimate of it. And in Fjord, it's continuous time. It's a continuous time flow. So there they actually also can work with dense Jacobians, and yeah, you don't have to compute the determinant there. We'll also get back to this. But first, let's look at coupling flows. I would say this is the most maybe popular type of flow. If you want to learn just one, I would think that's the one you should probably look at, because it's very practical. It gives you the fast and exact, fast in both directions that we talked about before, and the exact computation, and is relatively easy to implement compared to some of the other ones here. There's this one. How do we get this structure on the Jacobian? If we have some data X and we want to transform that to set, we start by partitioning the data, or the dimensions of the data, into 2 parts. You have some choice, but typically it's roughly 50-50. And then you transform the second half, and you do that conditioned on the first half. So you have a neural network that looks at the first half, spits out some parameters, mu and alpha, and then you transform the second half using these parameters. So I call it the inverse here because we go from X to Z. So the first part, you don't transform it, or that is, you identity transform that. And the second part, you use this mu and alpha that came out of the neural network, and you shift and scale using that. So you can use more flexible transformations than this is like an affine transformation. You can use something more flexible. You can use splines, polynomials. There's many things you can do. We won't look at that here, but that's also possible. But you can create quite good flows even with just the affine one. Yeah. So what I want you to do now is try to derive the forward pass of this, which is kind of the inverse of the inverse, and the Jacobian determinant. We'll take, I think we can take 5 minutes. No. Yes. So I think maybe we should get going again. The solution is here. This part shouldn't be too difficult. The identity transform part is trivial. It's still the identity transform. And this one is not too difficult. You can kind of move mu to the other side and then divide by e to the alpha, and you get this. And then the Jacobian determinant. There you have to realize that because the Jacobian is lower triangular, the determinant of it will be the product of the diagonal terms. And so the log Jacobian determinant will be the sum of the log of the diagonal terms. And in this case, that will be just these alphas. So it will essentially be the sum of the alphas from d plus 1 to d. And remember that these alphas are just output by this neural network. So it's super simple to compute this. Yep. You still have to do regular backpropagation through the network, yes. But there's no, I mean, you don't have to form any Jacobian matrices, and you don't have to explicitly compute any determinants. That's the benefits of this structure. And the other big benefit that I mentioned before is that this is fast in both directions. And the reason is that, I mean, here the neural network looks at this x1 to d. And if you're coming kind of from the other direction, you can imagine the neural network can just look at that part instead. And so it can spit out, it can compute mu and alpha regardless of the direction you're coming from. So is this enough? Can we just now stack more layers of this and it will be great? And you can see probably that there is, of course, a problem here. If we just stack them like this, we will keep transforming the same part, and this part will never be transformed. Not very difficult to fix this. We typically use something called permutation layers. And a couple of simple ones are the reverse and the shuffle layer. So these are also bijections, very simple ones. The Jacobian determinant is 1 when the log of that is 0. So the reverse is just like if there was an identity matrix, it would be like one's going this way, it's the other way, so you get the terms in the reversed order. And shuffle is similar, but you kind of sample a permutation. So importantly, you do this before training. It's not like in every iteration, but you sample a permutation and you keep that fixed. That will move the elements around. And then you can, if you then stack layers in between the coupling layers like this, then you will get mixing of the dimensions. So it's time for the coding session. So I'm going to show you the notebook. So we'll implement, as I mentioned before, coupling flow on 2D toy data. And the reason we're doing 2D toy data, not CFAR10, is that you can train the model in minutes instead of hours or days. So it's a bit more practical for a session like this. So there's 2 things you will implement. I will switch over to the notebook. You're going to make the coupling bijection and then a suitable network. So first, there's kind of 3 parts where we create the data set, we create the model, and then train the model. In create data set, you don't really have to look at this. We just create the 2 spirals data set. a train and test loader for that. And then we have a plotting utility that plots the data, and if you feed it samples, it will also plot the samples. So yeah, you don't really have to look at this part. And then if you go to the end, it's just a kind of standard training loop. We use Atom, and we train for 10 epochs. And this is just a very standard training loop. And you can see that the loss function we use is the negative log probability coming from the flow. So exactly what you'd expect. And then we optimize for that. And then after sampling, we will plot some samples from the learned distribution. So right now it's complaining, of course, because there's something that needs to be implemented, but it should work after that. And then here is the actual modeling part. First, this is a flow class, so it takes in a list of bijections. So that's the layers you want to use in your flow. And you can see it has the base distribution here. It's just a Gaussian. And then it has these two properties that we talked about, log probability and sampling. So log probability, it will loop through the bijections and sum up the Jacobian determinants. And then in the end, you will add the log probability from the base distribution. Sampling, you go in reversed order and you just pass through the inverse to generate the sample. So this is implemented. And here is the reverse shuffling or the reverse permutation layer that I just talked about. It's very simple. It just flips the input in both directions, and the Jacobian determinant is 0. Now comes the part that you will actually implement. And here is the start of a coupling layer. So it takes in a network here, self.net. And then what you're supposed to do is implement the forward and inverse pass for this one. And right now I've just set it to implement an identity transform. And so you're supposed to edit these so that, it should implement a coupling layer. The second thing is to implement a suitable neural network that will be given to this coupling layer. And here down here, the flow is defined. So this you don't have to touch. It's just stacking 4 coupling layers with reverse bijections in between. And to each coupling layer, we feed a neural network from this makeNet function. So I think that's it. And then there's just some things to note that I will keep on the slides. So here's the equations from before that we derived. So this will be useful for the implementation, of course. And one thing to note that might be a bit confusing is that forward and inverse are opposite in the notebook from this. So the forward in the equations here is what you should implement for the inverse in the notebook. So that's what's used for sampling. And what's this forward part is here the inverse. So it's from the data to the latent and the Jacobian determinant for that. So it's basically what you use for training, and that's implemented in the forward pass because that's standard in PyTorch. Final thing. Oh yeah, this is just like what they should return. So the inverse should return something that's, so B is the batch size and 2 is the dimension of the data. So B, 2, same as set. Other directions same, and also a Jacobian determinant. But this one should have, it should be 1 for each data point. So it should have shape, batch size. And just, this is the final thing. These are some potentially useful functions. So for the first problem, probably torch.chunk and cat will be important. So you can look up that in the documentation. And for the second part, not that important, but you can probably use nn.sequential. So you can just kind of linear or like stack layers sequentially, and you don't have to define a new class. So you can also look at that in the documentation. Yeah, and I think we'll take, or yeah. Oh, they don't have link. Okay. So we'll, yeah. Yeah, so you will send this on Slack. Yeah, so he will share the link on Slack for the notebook. And I think we can spend, yeah, let's say 45, 50 minutes, something like this. I will. Yeah, there's also a bonus part. If you're very fast, you can try to improve performance and so on. You can look at that as the final point. Hello. I won't stop you just yet, don't worry. But I just wanted to see how many people have kind of made it work. Can I just do a raise of hands? I just wanted to see. I've managed to train something. A few people, okay. Yeah. But many people still aren't there. So I think maybe I will just show you the solution, put it up, and then you can still have some time to take inspiration from the solution and then see if you can train it on yourself also. So, why is this not working? Yeah, so here's the my solution. It of course doesn't have to look exactly like this, but I'll just quickly go through it, and then you'll have some more time to code. So you get the input X, and you chunk it into two parts. I call it ID, the one that will be identity transformed, and X2, the one you will transform. And then you pass the identity one to the network. That's the what it conditions on. It outputs P, some parameters, and then I just sorry. Zoom in, yes. Maybe like that. If I also go full screen, is that better? Yep. Yeah, so I pass the identity part into the neural network. I get some parameters, and then I again chunk that into two parts, log S and B. So that's what's called alpha and mu in the notebook or in the slides. And then do the formula. So you scale by the exponential of this, and then shift. And then I make set by concatenating the identity part back with set2, the transformed version of x2. And then the log Jacobian determinant is just a sum of the alphas or the log S. And that's it. And then the inverse part is kind of the same kind of logic. So if you get the forward part, it should be fine. And for the make net, I mean, of course, you can implement that in many different ways. The important part to realize is just that we have two dimensions and we're splitting it in two. So the input should be one-dimensional. So it should take a one-dimensional input. And then you can construct some kind of MLP, for example. And then the output so you're outputting parameters for the other part, and there's two parameters, mu and alpha. So you should output two there. And that's the important part. Of course, the exact structure you can change around a bit. So I think you can take a few more minutes. You can try to take inspiration from this and see if you can get the code running. All right, maybe we should continue. So I'll first just show so this is samples before training. So it's kind of almost Gaussian, but of course something happens in the transformations. And then here's the training loop. And here's some samples. I mean, they don't look great, but you can see that it's doing something. And I haven't really worked on tuning this at all. I just made the first run, and it seemed to be doing the right thing. So you can work on improving this by training for longer and improving the neural network and doing some form of improvements. But you can see that it's doing better than what probably a Gaussian would do, and it's starting to capture some of the structure. Probably just training longer would also help a lot. Yep, and then all right. So now you've hopefully managed to implement some flow on toy data. So that had shape b, 2. So you might be wondering, how would this work if I wanted to implement it on images? Because most of the papers you'll read on flows, they will work with images for some reason. And for example, CFAR 10 would have, it typically has shape, or it has shape, the batch size, and then it has 3 channels, and then it's 32 by 32 images. So what changes would you have to make to train this on images? First thing is, how do you do the splitting? When you have only 2 variables, it's obvious because there's only one way to split it. Now there's many ways of doing it. In the real MVP paper, they did a few different ways. So they did splitting along the channels, and they also did some checkerboard masking kind of stuff. In the follow-up paper, Glow, that improved on real MVP, they only did splitting along the channels, and actually they showed that they improved performance over real MVP, and they just used that. So I would say that's kind of the recommended way to do it. It's much easier to implement also than the other strategies. The other thing that is maybe obvious is you probably wouldn't use an MLP if you're working with images. You would use something that works on images, like convolutional nets, maybe some vision transformers or something now. The other thing is there's more types of permutations. So we mentioned reverse and shuffle before. This is from the real MVP, from the Glow paper, where they show that shuffling works better than reverse. And then they introduced this new thing, which they call 1-by-1 convolutions, which works even better than that. And what that is, it's kind of a learnable permutation layer. So you don't have to fix it beforehand, but you learn it. And it's literally what it says. It's a 1-by-1 convolution. So kind of within the set of all the matrices you can learn, all the permutation matrices will be in there. And they simply rely on the fact that typically you don't have that many channels. Could be like 3 here, and so that will be a 3-by-3 matrix. So it's not that expensive to invert or compute a determinant for, even just a straightforward thing. And they also have ways of scaling it using the LU decomposition and so on. But so if you're working with images then this is probably a good idea to use. Last thing is images aren't really continuous. They are stored in a discrete way. They are the pixel intensities are stored as integers from 0 to 255. And so another trick you need that we'll get back to a bit later is dequantization. Essentially a way of turning this discrete data into continuous data that you can train on. Yes, so that takes us back to this slide. Now we looked at coupling flows. And now we'll look at autoregressive flows for a little bit. So they are closely related to autoregressive models. So here's a figure. On the left, you have an autoregressive distribution. So if you have kind of the data dimensions down here that you're predicting sequentially, you can see that, for example, this orange thing here, if that's the parameters of the distribution for this one, it's informed by these are like hidden units in the neural net. It's informed by these, which are informed by the data coming before it. You could do the same thing with the flow. You could have flow parameters that are informed by the data coming before. And now you have flow parameters, which gives you kind of the parameters you need to convert between X and Z. And so you might say, this looks very similar. Is there a connection? And yes, for continuous distributions, they are equivalent, meaning you can always represent an autoregressive distribution as an autoregressive flow. For example, if you have a autoregressive Gaussian, you would use a standard Gaussian base distribution and just shift and scale. So, and like, what's the benefit of autoregressive flows then? It's of course that you can stack these in layers. And you can just flip the order in between. So basically, you don't really have to process the data in a given order. So these have fast density computation because I can input some data down here. I can pass it all through the neural network, all in parallel, and I get all the green parameters in parallel. And then I take the data again and I transform it using the parameters. And this requires only one forward pass in the neural net. So it's relatively fast. If you want to sample from this, it's pretty slow because you have to do it one element at a time. So if I want to transform the second one, you see that it needs parameters that are conditioned on the first one. So I first need to transform this one down, and then forward pass to get the parameters, then transform this down, then new forward pass, and so on. And so it scales poorly with dimension of the data. Interestingly, with flows, you can do the kind of the inverse, where you don't really condition on the previous data elements, but the previous noise elements. And this has kind of the opposite properties, where sampling is fast. Now you can do that in parallel, but computing the density for new samples is very slow. So autoregressive flows are kind of more suited for training on data, because that you need to compute the density for when you're training. Whereas inverse autoregressive flows, not so well suited for that. However, they are very well suited for variational inference, because basically what you need there is fast sampling. And I think we'll get to that a bit in the end. Yeah, and just for comparison, there's coupling flows also, and they are fast in both directions, requiring only one forward pass. But of course, they are less expressive than the other two. The other thing you need, so if you decided to use an autoregressive flow, you need to have some kind of autoregressive neural network in it. And the first thing that might come to mind is recurrent neural networks like LSTMs, GRUs, and so on. But they are typically not used because they still require some kind of sequential computation inside on the hidden states. So instead, people typically use masked neural networks. So depending on what type of data you work with, there are different architectures, and there's a lot of literature here. I'm not going to give a full overview, just some highlights. So if you work with vector data, you can use MADE. It's essentially just a way of masking a feed-forward neural network in such a way that the output is autoregressive in the input. So like one of the outputs will not be connected to any of the inputs. Second output will be connected to one of the inputs, third one to the first two, and so on. So in some order, it will be autoregressive. If you're working with sequences like audio or text or something like that, you can use something like WaveNet. So that was for audio. And there they use a masked 1D convolutional network. And they mask the convolutional kernel in such a way that it's causal, as they call it. So it only looks at elements that came before. And they also use dilation, as you can see here. So you can exponentially increase the receptive field. And this works very well for audio. Images, you can use something like Pixel CNN. Also a masked convolutional network, but here in 2D. So if this is the convolutional kernel, you mask the lower part like this. And so you can see if you kind of slide the kernel over the image, it will be autoregressive in the raster scan order. So that's like from top left, and you go like left to right and top to bottom. And so if you mask all your convolutional layers in the network, it will be autoregressive. You can also use the transformer type architectures. For sequences, you could use essentially the decoder part of the original transformer architecture. So here you don't need the encoder and you don't need the part connecting the two. It's just kind of masked self-attention. And so essentially what you do is when you get the attention weights, the L by L attention weights, you mask them to be lower triangular. And in that way, you get an autoregressive distribution or an autoregressive network. And you can also do the same for images. And there's also loads of papers that have built on this and improved on these models. But these are some. So that takes us back to the outline again. We have now talked about coupling flows and also implemented. They are fast in both directions using this structured sparsity. And we have talked a little bit about autoregressive flows, which are either fast to compute the density for or fast to sample from. We have to choose. And now we'll look a bit at continuous time flows and residual flows. So continuous time flows, you might have seen this paper, Neural OD. It was the best paper award at NeurIPS 2018. And what they do is describe a kind of continuous depth neural network. So instead of having like layer 1, layer 2, it's kind of, there's a continuous time axis. And the forward pass is described by an ordinary differential equation. And so that's the one stated here. You have, so T is kind of the depth, and then set T, that would be like, think of it like the activation functions that change with time or with depth. And you can see like the x-axis here would be like one of the activations, for example. So how that changes as you go deeper in the network is given by some function that depends on the current activations and the time. And what makes it a neural OD is that they use a neural network for this. So the dynamics are described by a neural network with some parameters theta. And solving this forward would not be too difficult. If you put a neural network there, you could use the Euler discretization. That would be like equal size steps going forward, and then you would get a residual network. Or you could use some kind of adaptive solver to improve the computation. So that's not too difficult, but if you want to kind of learn the dynamics or like optimize this neural network, now you need to be able to backpropagate through it. And that's really what they did here. So they showed that you can define a second OD that goes backward in time. And that's kind of the continuous time analog of backpropagation. And so you can train your OD or like the dynamics of that to solve a given task. So like if you propagate to the output here and then you use that in some loss function, as you would typically do, you could backpropagate through all of that. So you can make classifiers or whatever with this. So we are interested in normalizing flows, and they also did not only this, which was very cool on its own, but they also introduced some more stuff, and that was the instantaneous change of variables formula. So that's really the continuous time analog of the change of variables formula. So they describe how the density, the log density of set changes as you go deeper in this transformation. I should also mention, like ODs they are invertible. So it's easy. Once you've specified an ODE, you can always just run it in reverse. So here, the log density changes according to the negative trace of the Jacobian. And the trace is, of course, I mean, that's just a sum of the diagonal terms. This is much cheaper to compute than the determinant. So that's interesting. Like by going to continuous time, the problem kind of gets easier, although now you have to solve some differential equations. But yeah. So this was built on in Fjord, where they introduced kind of a way to estimate this trace of the Jacobian for black box neural networks. So it means you can specify under some mild constraints any neural network F for the dynamics and train that as a normalizing flow. And what they use is called Hutchinson's trace estimator. And that says that if I take the trace of the Jacobian, or really the trace of any matrix, it's not specific to Jacobians, this can be written as an expectation with respect to some distribution, P of epsilon, of the matrix multiplied from both sides by epsilon. And you can really specify any distribution P of epsilon you want under the constraints that the expectation is 0 and the covariance is identity. So the first thing that might come to mind is, of course, is the Gaussian, and that's possible to use, and they also did that. They also used, I think, the Rademacher distribution, and you can also come up with other ones. Yeah, so you might say, okay, that looks cool, but it seems I still have to compute the Jacobian here, and that was supposed to be kind of expensive and hard. But actually, that's still true. It's still quadratic in cost, but computing a vector Jacobian product can be done in linear time. So if you already know the vector that you want to multiply the Jacobian with, as you do here, if you sample Monte Carlo sample from P epsilon, then you can ask for the vector Jacobian product with that epsilon. And that is you can do in linear time. So that means it's actually possible to get unbiased estimates of the density here, really. If you solve, so I mean, it's kind of a new differential equation you have to solve with this, also the log P. But in a practical way, you can do unbiased estimates of that. And yeah, this also interestingly connects to score-based and diffusion models that also I think Rihanna talked about. Exciting new development. A lot has happened in the last 2 years. And if you look at this Song et al. Paper 2020, it was best paper award at ICLAIR 2020, I think. They use, or 2021, they use stochastic differential equations to model data, and then it's like you kind of diffuse according to a stochastic differential equation, and you learn to denoise according to that, and so on. But then after training, they can actually convert the stochastic differential equation to an ordinary differential equation that has the same marginal distributions as the stochastic differential equation. And then they can use that to compute the exact log likelihood after training, and also sample from that. And I think they say that that typically generates a bit better samples than the original one, presumably because there is less noise in the process. So yeah, I'm not going to go into detail on that, but I think it's a very interesting connection. So if you find that interesting, you can go look in that paper. So residual flows, another class. They rely on invertible rest nets. So here is what one layer looks like. You have set, which is output as some f of x, which is x, plus some residual function h of x. So that's exactly what a regular rest nest look like. And the condition they found to make this invertible, or to have it that it's theoretically invertible at least, is that h is contractive. That means the Lipschitz constant of h is bounded by 1. Essentially, the function shouldn't change too quickly when you change the input, essentially. So how do they enforce that? They use what's called spectral norm, and that comes from the GAN literature. And inside it really uses power iteration, which is a way of estimating the largest singular value. And so you run that for some iterations and kind of normalize by that to keep it approximately contractive. during training. The second thing you need is the Jacobian determinant, of course. And they show that this can be written as such. It's a trace of an infinite sum with alternating terms with alternating signs, and the Jacobian of h coming in there. So how do they compute this? Well, first they use Hutchinson's trace estimator for the trace. And second, for the infinite sum, they simply truncate it to some fixed number of terms. That's, of course, an easy solution. The problem is that introduces some bias. So in follow-up work, they showed that, so in blue is their follow-up work. They show that kind of the training loss and the test loss seem to match reasonably well. Whereas in the biased case, red, you see training loss goes down, but it kind of keeps going down, and the test loss kind of becomes unstable and goes up. And what they say that this is due to the bias. And essentially neural networks are very good at hacking whatever flaw you have in your code. And it's really, that's what's happening. It's optimizing for this bias. So their solution was, of course, to get rid of the bias. And they do that using this crazy trick called the Russian roulette estimator, which says that you can estimate a sum of an infinite sum of all alternating terms using the expectation with respect to a distribution Pn that has support over the integers. And then you in the sum here only goes up to n. And then you have the terms and then normalized by this term. So when you Monte Carlo sample from this, it means you will sample a given n and then truncate the sum at that term. So you will kind of stochastically truncate the sum. And if you do this, you will get an unbiased estimate. And I think in the paper they used a geometric distribution for this PM. So in addition to that, they introduced some other things. For example, memory efficient gradient estimators for this Jacobian determinant and so on. If you want to know more, please look in the paper. I won't go more into detail. So that takes us again back to the outline. So we looked at now continuous time flows and residual flows. They can work with dense Jacobians, and they will get around it by either considering the continuous time problem, where you only have to work with the trace, or invertible rest nets, where you kind of get this infinite sum that you can somehow truncate. And now we'll look at discrete flows and surjective flows. So far, we've only talked about continuous flows, that is, flows on continuous data. But if you have discrete data, how would you use flows for it? So one thing you could do is have a discrete, some discrete bijections and also a discrete base distribution. And in that case, you don't have any notion of volumes. There's no Jacobian determinant in this case. So you kind of just transform your x to the latent space and evaluate the base density there. And so it might seem that this is much simpler than continuous flows. And well, in the sense of Jacobian determinant, you don't have to worry about that, so it's simpler. But it has its own set of problems. You need to, I mean, it's hard to define discrete bijection. So it's very limited what you can do. You can essentially only kind of permute probability masses around. And the other thing is how, optimization. How do you optimize it? So we'll look at a couple of papers. Discrete flows, they considered flows for categorical data. So think like text. There's a fixed number of categories with no order. And they consider using coupling flows or autoregressive flows where the element-wise transformations are given like this. So xt is your categorical variable, and then you shift and scale that also by some discrete variables. And then you use modulo k. So k is the number of categories. This turns out to be an invertible transformation. So yeah, you can use that. However, it's not obvious how you would optimize this because it's a discrete operation, so it's non-differentiable. Or really, what I should say is the neural network outputs some parameter theta that you take the argmax of, and that will give you your mu d. And this is not differentiable. So how do you get around that? Because you need it to be differentiable to train it. Basically gradient descent. What they use is called the straight-through estimator, which is by Benjo et al. 2013. Didn't put the reference, but what they do is you kind of, when you do the backward pass, you just pretend like you use the softmax. So instead of the argmax, which is discrete, you use the softmax with some temperature tau. And this is differentiable. And as tau goes to 0, this goes towards the argmax. So at tau equals 0, it equals the argmax. And so it's kind of easier to optimize for higher tau, but it's closer to the true objective for smaller tau. So what they do is start with a higher tau and then decrease that during training. Another paper came out around the same time, also on discrete flows, but they considered as a slightly different problem. They consider the case where you have the integer line. So it's an ordinal problem where the categories have an order and it's all the integers. And for that, they also use coupling flow or altruistic flow, where the element-wise transformation is just this. You take the input and you shift it by some integer amount. And again, the neural network will output some theta d that you have to make discrete. So you use a rounding operation to get mu d. And so again, you have the same problem that this is not differentiable. So how do you get around it? Same trick. Straight through estimator also. So that it's essentially when you pretend in the backward pass that you did something else than you did in the forward pass. And here it's even simpler because you just pretend like you didn't do the rounding operation, that it was just identity. So this, of course, introduces some bias because you're not optimizing the loss or the objective that is the true one. And they discuss this in this paper. They show that as they stack more layers, more flow layers, in the continuous case, performance keeps improving. However, in the discrete case, it first improves, but then as they stack more layers, it starts to degrade the performance. And they speculate that this is due to gradient bias accumulating through all the layers. So there's like some gradient bias in every layer, and that kind of gets worse with depth. Yeah. So that takes us to surjective flows, which was introduced in 2020 by Nielsen et al. So that's Nielsen, me. And here we showed how you can also introduce layers in a flow that are not invertible. And you could still have like kind of the forward, the inverse, and something along the lines of the Jacobian determinant. And yeah, so these surjective layers, they're surjective and non-injective, characterized by you can have two inputs that can map to the same output. So obviously that will not be invertible, but every surjective mapping has something known as a right inverse. That is a mapping that goes the other way, such that when you go the other way again, you will get back to the same point, essentially. And this is, of course, not unique. So in this case, when you can go from this point, you could either map back here or you can map back here. So what we do is define a distribution over all the possible right inverses, and we call that a stochastic right inverse. And that's essentially how we invert this. So some examples: rounding, that is not invertible. If you take the floor operation, any number between 5 and 6 will map to 5. So when you go the other way, you don't know where you came from. The stochastic inversion of that would be to map to a number between 5 and 6. And that, interestingly, corresponds exactly to dequantization, which is a trick that has been around for a long time. And it's been used, at least initially, kind of without a good explanation other than that if you don't do this, it will collapse. And because you kind of, if you have discrete data like this and you try to train a flexible continuous distribution on it, it can just place like a very peaky, like think a mixture of Gaussians with a peak on every integer value, and you can get very good log likelihood performance, even though you're not really modeling the distribution in any way. But if you take the integer data and you add uniform 0-1 noise, so you kind of fill out the continuous space, then you get a continuous distribution here. And if you train the flow on that, it's stable and things work out. But yeah, interesting, that corresponds to, you can really be expressed as a surjective layer. Another thing you can do is what I call tensor slicing. So it's kind of written in programming notation here. If set is 100 dimensional, you can slice away the last 50 elements and X will just be 50 dimensional. Obviously, this is also not invertible. When you go the other way, you don't know the last 50 values. So you have to stochastically infer them. And if you do that, so that is one surjective layer, and it essentially corresponds to these papers that were introduced around the same time in 2020. And it helps, get around some problems with bijective layers. We won't go into that. And finally, the argmax layer. So we introduced this after the survey flows paper, and it kind of directly builds on that. And here we said that you can you can convert between a continuous and a categorical space. So rounding kind of converts in the ordinal sense between a discrete and continuous space, but this converts in the categorical sense. So if X is, it could be text, it could be a character, for example, then you can have a continuous space that is, if it's, you can have like 27 characters. You have a vocabulary of 27 characters, then you would have a continuous space of dimension 27 in the simplest case, and the argmax of that will be like the outputs. And of course, in the paper, we consider various ways of doing the stochastic right inverse for this operation. And so we were able to train flows on text data. And so we take you can train any continuous time flow or residual flow, coupling flow, autoregressive flow, any kind of standard flow, and just add an argmax layer to convert between the continuous and the discrete space. So here are some samples. So we were able to get something reasonable with this. And you can come up with many other ones. Yep. So that's it for discrete and surjective flows. So in the discrete flows case, you don't have any volume. And it's kind of hard to define discrete transformation, but and optimization is hard, so you have to use a straight-through estimator. Yeah, question? Yeah, exactly. Yeah. So if you have data that is both continuous and discrete, you can by using essentially the argmax on the discrete part, and then you will kind of map everything to a continuous space, and then you can model it there. And then, of course, the other way it's defined by just taking the argmax of the continuous part that will map to the discrete part. Yeah. So that's it for the main part. We have a lot of time, so that's good. Then we can look a little bit at the bonus. The talk is not over. So we'll look at how to use it in variational inference, flows in variational inference. So far we've considered, or we really just looked at normalizing flows in general, but kind of all of the time we were thinking about generative modeling or density estimation, where the goal is to try to learn the data distribution. So yeah, you have a flow like this, as you've seen before. And you do this by minimizing the scale divergence. And for those that don't know, this corresponds exactly to maximizing the likelihood. So essentially, you have samples from Q here. So this the expectation will turn into a sum, and you can drop the entropy term, and then you just have maximum likelihood there. Now we'll look at variational inference. So we have a new kind of target density. Now we want to approximate the posterior distribution. So this can be, so this is like a distribution over the parameter. So you have a Bayesian model. I guess you have talked a lot about this in the last few days. You have a distribution over the model parameters, condition on the data. And this is intractable, so we want to approximate it. So now we will have a flow like this. So it's exactly the same logic, but now I've changed the notation, so it's epsilon up here. And then we generate some parameter configurations down here for our model. And now we will minimize the KL divergence the other way around. So now we are optimizing, like over here, we were optimizing this. The second term was what we were training. The flow is there. Now the flow is in the first part. And that puts some different kind of, you want different things from your flow. So here you want fast, kind of this inverse transformation from X to Z, you want to be fast. Now you want from epsilon to theta to be fast. And of course, this minimizing this KL, you don't do it directly, but as you've probably learned, I would imagine in the last few days, it's done through the elbow. So maximizing the elbow is equivalent to minimizing this KL divergence. So yeah, we have some approximate posterior Q of theta. It has some parameters lambda, and we want to make that approximately equal to the posterior. The one popular way of doing it is the mean field approximation. The term mean field comes from physics, but really what it means is just that it's a factorized distribution. So you have one Q for every parameter. And like before the modern reparameterization type variational inference, you could solve, if you fix all the dimensions except one, you could solve for the functional form of that Q. And so that's how they used to do variational inference. It's not really used that much anymore, but people still kind of use this approximation because it's of course still very simple. And a very common choice is to just have, you guessed it, a Gaussian for each Q. So that will essentially mean instead of just training your theta, you will have one estimate of its value and one for the uncertainty in that parameter. And as we mentioned before, you typically fit this Q to P by minimizing the KL divergence. And so for a mean field approximation, what does that mean? So is the mean field approximation a good approximation? Yeah, probably typically not, right? It has no, it can't model any correlation. So even if your true posterior is this bivariate Gaussian, so that has some correlation in it, the approximation can't model that. And also, since you are optimizing the KL divergence in this direction, the approximation will tend to be mode seeking. So it will tend to focus in on the kind of central part there. And it's penalized hard if it places mass outside of where the exact posterior has support. And what that means for the approximate inference or Bayesian inference part is that it will tend to underestimate the uncertainty. So you probably have learned a reparameterization trick. So when you want to implement the mean field Gaussian, you do it by sampling from a Gaussian and then transforming by shifting and scaling this epsilon to get this Gaussian distribution down here. And you might say this looks a lot like a flow. And yes, it is essentially just a very simple flow with kind of just an affine layer. So we can, of course, generalize this to use some kind of invertible neural network here, f of lambda. And to compute the density, we will again use the change of variables formula. So kind of if you already know how to implement the mean field Gaussian approximation with the reparameterization trick, and you know flows, then combining them is very straightforward. It's kind of just directly extending this computation graph that you have over there. And so we can build more flexible posterior approximations very easily. So what kind of flows do we want to use in this case? Desired properties is that we want to be able to sample fast, or the kind of the forward direction from epsilon to theta. And we also want to be able to compute density. However, we don't have to compute the density for novel samples. So I will never give you a sample and ask for the density. We only want the density for the samples that we are generating. And this we can do only using the forward transformation. So we don't really care too much about the inverse going up to set, or to this case epsilon, to be fast, or even you don't even have to be able to compute it. Yeah, so we only need the forward direction. So if you remember this picture from before, we see that, of course, the autoregressive flows would be horrible here, but inverse autoregressive flows are a perfect candidate. There you can do the forward pass, or like the forward transformation in a single forward pass in the neural network. And so inverse autoregressive flows are a perfectly good candidate for variational inference. So could we use some other flows? So here's also something you might remember from earlier slides. Inverse autoregressive flow sits there. You can use really any of them. You could use coupling flows, but inverse autoregressive flows are just more expressive, and they have really no drawbacks in this case over coupling flows, except for maybe they're harder to implement. But once you've implemented them, they should kind of just be better. You could, of course, use fjord or residual flows, etc. And then we have the ones up here that I didn't talk about, and they are actually also quite often used for variational inference. So planar and radial flows come from this paper. It has variational inference in the title, variational inference with normalizing flows. And also Sylvester flows, also introduced for variational inference. So these are also popularly used. But they are less flexible than inverse autoregressive flows. They're kind of simpler. So let's look at a couple of examples. We'll look at variational autoencoders and Bayesian neural networks to see how you would apply flows in the variational inference there. So variational autoencoders, I've drawn it kind of like a flow here. You could think of this as the kind of the decoder and the encoder. And yeah, so you have the prior is a Gaussian 0, 1. And then you have a likelihood that is, this is the decoder. It's a distribution over X that is conditioned on set. And here you use a neural network with parameters theta to kind of predict the parameters. So this could be like a Bernoulli or a Gaussian or something like that. And then you could do, of course, the mean field approximation. This is the standard thing you will see in the original variational autoencoder paper, and also in most work. That's what people are using. But this could, of course, be extended to using a flow. So now you would have kind of, so the neural network would come in so it will be a conditional flow in this case. And the neural network will kind of put out some context that can be used in the flow when it's transforming epsilon to set in this case. So this is a figure from the inverse autoregressive flows paper. So they considered exactly this variational autoencoder problem. And this is how they structured it. So you have, so the encoder, it will look at X, goes into the encoder network, and you get some sigma and some mu. And you multiply your epsilon, like shift and scale the epsilon with that. If you stop there, you have the mean field Gaussian case. But they don't stop there. They also put some inverse autoregressive flow layers. So they keep transforming set. And you see that the encoder network spits out also one more thing, and that's H, which is some context that will be provided also to the inverse autoregressive flow layers. And so each layer will put set into an autoregressive neural network. And here they use MADE that we mentioned before. And from that, you will get some sigma and mu that is computed autoregressively. And you again shift and scale your set by that. And yeah, this autoregressive, the MADE will also have to be a conditional MADE that takes in some context H. So it's a little bit kind of tricky to implement, but yeah, you can get much more flexible posterior approximations. Other example, Bayesian neural networks. So here you have a likelihood like this. So it's a standard thing. It's a product of all the, so you have pairs of data, yn, xn, and then you have a distribution that kind of yn depends on x, and also the theta, the parameters of the neural network. This could be many things, for example, Bernoulli or a Gaussian, depending on your data. So, I mean, this will be a binary classification problem, this will be a regression problem, and so on. And mu n is, so the mu n in these distributions will then be predicted by the neural network. Input xn, parameters theta. And so, yeah, your theta will be just the weights and biases in all the layers of the neural net. So this is exactly a regular neural net. If you just now train this with maximum likelihood, this corresponds to classical classification or regression. What makes it a Bayesian neural net is that we now have, of course, distributions on the parameters. So instead of just these point estimates, we have distributions here. And we get that by placing a prior on the parameters of the neural net. And typically what is used is, again, just a simple Gaussian. What prior should you use on the parameters of a neural net? It's a very difficult question. And yeah, the people have been discussing this a lot, but commonly used is just a simple Gaussian. And it seems you can still get things to work with that. So for the posterior approximation, I mean, of course, the posterior is very intractable in this case. So you can again use, of course, mean field, and that's kind of easy enough. For each parameter in the neural network, you get an estimate of its value, but also of its uncertainty. But as we talked about before, the mean field tends to kind of underestimate uncertainty, and it kind of will focus in on a smaller Gaussian distribution than the complexity of the true posterior. So can we use something more flexible? Yes, of course. We can use a flow. And yeah, everything is kind of the same here. You can transform an epsilon to the parameters of the neural net. However, there's a problem here. Not a theoretical one, but a more practical one. And that's that the number of parameters in a neural network is typically very large. So you can have millions of parameters. And so if you're going to have a flow that transforms like a million dimensional noise to a million dimensional parameter configuration, you're going to have a neural network in there that has to have a million dimensional input and million dimensional output. So it doesn't scale well. And so it's hard to really apply flows directly for Bayesian neural networks if you kind of do it in the naive way. Unless you have a really small Bayesian neural network, then it could be doable. So how do you scale this? So this is kind of separate from the flow part, but it's a very nice trick that is useful for scaling Bayesian neural nets. It's called a local reparameterization trick. And so this is like one layer in the neural net, and say you have this variational distribution on the weight and bias. You sample from those, and then you compute the activations or the output from the input X. And what it says is that if this has a Gaussian distribution, which it does in the mean field case, then you can actually directly compute the distribution on the activations H, which will also be a Gaussian. And the benefit of this is now you can sample, instead of sampling all the weights and biases, you can just sample the activations. And that seeming at first sight might not seem like such a big win, but it has much lower gradient variance. And it comes from that essentially, especially for higher batch sizes. So essentially there will be lower correlation between the gradients coming from each data point in your batch. So in this case, if you just sample the weights and biases directly, they will use the same weight and bias. You will use the same for all the data points in your mini batch. But here you effectively get independent weights and biases for each data point. So you can do this kind of variance covariance decomposition and see that it helps a lot. And also in practice, you will see it. I've also tried this, and it's much easier to train in this case. And then there's this paper, and this actually uses normalizing flows for Bayesian neural nets, called multiplicative normalizing flows. And this is a way to, in a more scalable way, use flows for Bayesian neural nets. So what they do is, for this W, they define, they introduce an auxiliary variable that they call set. And they use a flow on that part. And then the distribution on the weights are conditioned on the this auxiliary variable. And you can see in here that set only has the same dimensionality as the input to the layer, and not input times output. So it's much lower dimensional. And so that means, it's much more scalable. And so you can actually apply it to real neural networks. And in this case, as they show, that you can still apply the local reparameterization trick from above. And of course, you now get a much more flexible distribution queue. And so on the right here, you see kind of a standard mean field Gaussian. You see, it's maybe a bit hard to see, but there's some red points here. And you can see the uncertainty is a bit lower. But as soon as you introduce this, of course, because of the mean field tends to underestimate uncertainty, as we mentioned, this will estimate the posterior distribution better. And you can see that uncertainty goes up. And so that's what you would expect. So you have a better approximation of the true posterior. I think that's it. So, thanks for listening. I have time for questions if there are any. Otherwise, we can take an early break. Yep, there's multiple, but yeah. So you mean to just have a Bayesian inference on the last layer? I've also seen that, but I don't know if anyone has specifically considered to try with flows. That could be, yeah. I guess that would also make it more scalable because it's lower dimensional. So that's also something I could try. Yeah. Yes. If you just do, sorry. So how does the Laplace approximation compare to this? So it's kind of, in a sense, maybe a bit more similar to the mean field. So I mean, you get a Gaussian approximation there. So, but you don't fit it using the KL divergence. So the approximation won't be optimized using the KL divergence. You just optimize till you get to the mode of the posterior. And then you compute kind of the curvature there and use the Hessian to define the covariance in the Gaussian distribution. So it's, yeah, I would maybe say that's a bit more, it's not clear what it's optimizing for. It's kind of a heuristic approach to get a reasonable, maybe reasonable approximation of the uncertainty. But it's less obvious how you would extend that to flows or something like that. Yes, I think unless there are more questions, then we can just, okay, one more. Yeah. Are you thinking that the normalizing flow should, I mean, you're deterministically changing the states in the latent space or in the, like the, yeah. Yeah, so I guess you could do that. I think if you look at the which paper is it? I think the neural ODE paper, they consider, but there is continuous time. So you learn like an ODE in the latent space, and then you have like a emission distribution. So you can actually model their irregular time series. It's very interesting. So you can also model like the like the point process of when the observations occur. So I guess that would be one connection. So that's really using a flow in the latent, or like for the evolution. For like discrete ones, I haven't really seen it, or like discrete time flows. But you could probably also do it, but I would imagine it would be harder to. Yeah.